Well, from the last speaker of morning section, David Hicks, he's going to talk about this regular ideal and closure.
Thank you. I really appreciate being able to give a talk, and I'm also very happy to be here. It was a little challenging to get here with the airlines. All right, so I want to talk about some work that John Brown, Adam Fuller, and Sarah Resnikoff and I did. And we've done two segments of the project, and I'll talk to you about some of each. And so the idea is we had an inclusion of one C-star algebra sitting inside another, and we wanted to understand the relationship between regular ideals in the big one and also regular ideals in the smaller one. So I better remind you about some things. So for me, an inclusion is just a pair of C-star algebras. I want to write the big one first and the little one second. And I'm going to assume that's more, this is more for convenience, I think. I want to assume that you have the approximate unit property. So in other words, the little algebra contains an approximate unit for the big one. And it's regular if the family of normalizers, that's just everything in the big algebra that conjugate the little one back to itself, has dense span. So I'm not always going to assume that B is abelian. So sometimes it will be and sometimes it won't be. And I want to understand the relationships between the regular ideals of A and the regular ideals of B. So let me remind you what a regular ideal is. If you have any C-star algebra and just any old subset, the annihilator is, I'll write it as X perp. It's just everything in A. And when you multiply A times any element of X, or on the other side, you get 0. And I'm going to be talking about annihilators with respect to various subalgebras. So if you have a sub C-star algebra, I'll write an annihilator with respect to B, and that's just the intersection of the annihilator and the big one with B. So Hamana says that an ideal is regular if it's equal to its double annihilator. Okay, and I'll write our ideal for all the regular ideals. And it turns out that the regular ideals form a Boolean algebra under what you might the expected operations. The meet is the intersection, the join is the closed linear span, and the not is just the perp. Okay, and if you're going to be talking about relationships in an inclusion between ideals in one big one and ideals in the little one, it's very helpful to know that you have what's called the ideal intersection property. And that just means that if you have a non-trivial ideal upstairs, then when you intersect it with the smaller algebra, you get a non-trivial ideal. And it's always good to look at the commutative case first. And it turns out that topologists knew about this, but I didn't know about the topology work, so I sort of rediscovered it. And then it also follows from sort of general work of Excel. But let me tell you about what happens in the commutative case, and there are various authors here. So you have an inclusion with the big algebra being abelian and having the ideal intersection property. If you start with a regular ideal upstairs and you intersect it downstairs with the B, turns out you get a regular ideal. On the other hand, if you start with a regular ideal downstairs, then you can look at its double annihilator in A, and that turns out to be a regular ideal in A. And this mapping, when going from J to J intersect B, is a Boolean algebra isomorphism, and the inverse is this double annihilator. Okay. So it's natural to want to look for non-commutative cases. And so for that, I need to, I'll be needing to talk a little bit about a star semigroup of normalizers is a generating star semigroup if just span is equal to A. And an ideal in the small algebra is invariant under this family of normalizers if what you expect holds. Whenever you conjugate by a normalizer, you stay within the ideal. And I'll write regular ideal invariant for all invariant regular ideals in B. And lastly, I'm going to need to talk about conditional expectations. So a conditional expectation is n invariant if whenever you conjugate by a normalizer and then expect you get the same things if you first expect and then conjugate by the normalizer. And I'll usually just say invariant instead of n invariant. Okay, so here's our first non-commutative result. And so I'm going to have the setup is you have a regular inclusion with the ideal intersection property, and you have a generating star semigroup and a faithful n invariant conditional expectation. I'll call that E. It turns out that the regular invariant, the invariant regular ideals turn out to be a Boolean algebra, same operations. And if you start with a regular invariant ideal downstairs in B, if you take a look at everything in the big algebra, when you expect A star A, and you land in K, that turns out to be a regular ideal in A. And the mappings that you go from a regular ideal in A to downstairs to a regular ideal in B by intersection, that turns out to be a Boolean algebra isomorphism, and it turns out the inverse is this using the same formula that I had before. So you can start with a regular invariant ideal in B, look at everybody that expects with A star A into K, and that gives an isomorphism. And you might have expected that you would use this double perk formula that I had for the commutative case. And it turns out that that is true, that works. I showed this result to Rui Excel, and he liked it and greatly generalized it. There's a reference for it on the archive. He didn't need conditional expectations or regularity, and he used a slightly different notion of what are invariant ideals downstairs. But under the hypotheses of theorem A, he used he used the double annihilator to go back, but it turns out that that's exactly the same. So under the hypotheses of theorem A, you have this relationship. And this can be used to prove that the ideal intersection property passes to quotients sometimes. So here's the setup for that. If you have a regular inclusion having the ideal intersection property upstairs, you take you assume you have a generated star semigroup and an invariant conditional expectation. Now, if you start with a regular ideal, then you can form the quotient A mod J and then B mod B intersect J. And it turns out that when you quotient by a regular ideal and can get a new inclusion, you have the ideal intersection property. And I like that theorem because it allows you to prove a result that I think is interesting. So for Cartan inclusions, so now D is abelian and C is a Cartan massa sitting inside the C star algebra C, and you have a regular ideal in C. Well, when you take the quotient, you build the quotient inclusion, you get a Cartan inclusion. The conditional expectation is what you expect it to be. You just take a coset and you take the corresponding coset of the expectation. But you need theorem B to get faithfulness. So we wanted to, our second bit of work, that was our first. Our second bit, we wanted to extend this to where settings where conditional expectations needn't to be present. And for me, I like settings where I have something called a pseudo expectation. So I'm going to tell you about that, what that is. So you start with any inclusion, and I have the injective envelope of the little guy, and you have an embedding of B into its injective envelope. This was developed by Homana and others. But a pseudo expectation is just a contractive, completely positive linear mapping from A into the injective envelope of B, so that it extends the embedding of B into its injective envelope. And the advantage to pseudo expectations is they're always present. That's the injectivity that you use for that. And sometimes, usually there are many pseudo expectations, but sometimes there's only one. And there are interesting cases when there are only one, and I'll call that the unique pseudo expectation property. And sometimes that unique pseudo expectation, when you only have one, is faithful, and I'll call that the faithful unique pseudo expectation property. And the note on the bottom here is just to point out that pseudo expectations generalize conditional expectations. All right. So I want to say something about regular ideals when you have a pseudo expectation. Before I talked about invariant conditional expectations, it turns out there's a notion of invariant pseudo expectations. The issue is you can't multiply element normalizers in the injective envelope of B. So you'll remember that I had to factor out, but you can still get a notion of invariant pseudo expectation. And it's not a surprising notion. So here's the result. If you have a regular inclusion and you have a generating star semigroup and you have an n-invariant pseudo expectation, then you can do the same kind of thing that we saw before. You can take a regular ideal intersected with B, you get a regular invariant ideal, and that's a Boolean algebra isomorphism. But now the inverse map is you can take an invariant ideal in B, and you can take a look at everything so that the pseudo expectation lands in the image under the embedding of K. Okay, you take K and you push it into the injective envelope, and then you take its double annihilator within the injective envelope. So that's the inverse. So this generalizes theorem A. And I want to talk a little bit about what you can do when you have the B being abelian. So I'm going to tell you a little bit about that. So here, if you have a regular inclusion with an abelian D, so a triple is a Cartan envelope for this inclusion. If A and B is a Cartan inclusion, and I'm going to let E be the conditional expectation, that's turned out to be unique. Renault proved that they're always unique. And I'm going to ask that alpha be a one-to-one star homomorphism that carries normalizers in the original inclusion to into the normalizers of the Cartan inclusion. And that automatically gives you that alpha carries D into B. So D is going into B. And I asked that B alpha of D has the ideal intersection property. And lastly, this is a generating property that A and B are generated by alpha of A, the image of alpha of A, and then you expect. And then on the other side, you take this B and together with alpha of C. So basically, you're enlarging the diagonal, if you will. And so that's what a Cartan envelope is. And it turns out that if you happen to know that you have a Cartan envelope, then it's unique and it's the smallest Cartan inclusion into which C and D regularly embeds. And now I can tell you a little bit about what happens now. Oh, I forgot to mention, you can characterize when you have a Cartan envelope. The Cartan envelope exists if, when you take the relative commutant of D inside of C, that be abelian, and both C together with its the relative commutant of D and relative commutant of D and together with D inside of that have the ideal intersection property. And the last condition is that you have a faithful, unique pseudo expectation property. So these three conditions are equivalent. And if any one of those conditions hold, I'll say that the C and D is a pseudo Cartan inclusion. Okay. All right. So there's a structural relationship between the ideals in regular ideals of C and the regular invariant ideals in D. And I want to describe that. And so here it is. So from theorem D, we know that the regular ideals of C and the regular invariant ideals of D are isomorphic. On the other hand, from the same theorem A, I know that the regular invariant ideals in B and the regular invariant ideals in A are isomorphic. And the middle are isomorphic by generalizing the commutative case to study just invariant. So we get an isomorphism of the regular invariant ideals of C and the regular invariant ideals of A. And I think that's kind of interesting because it's telling me that there is a relationship. There's some structural relationships between a pseudo-Cartan inclusion and its Cartan envelope. Okay, and so I want to know what happens with quotients in pseudo-Cartan inclusions. So in pseudo expectations as well. So if you start with an inclusion having the unique pseudo expectation property. So there's only one pseudo expectation. If you have an ideal in the big algebra whose intersection with a little algebra is regular in B, then it turns out the quotient inclusion has a unique pseudo expectation, but it needn't be faithful. We don't know that it's generally the faithful property goes through. And I just wanted to mention that this is false if I don't assume that B is regular and a regular ideal and J intersect B is regular. So what happens with the faithful unique pseudo expectation property? Well, if you have an inclusion and you have the faithful unique pseudo expectation with the pseudo expectation phi, then it turns out that if you have a regular ideal, that if you have an ideal so that its intersection is regular, then the quotient inclusion has the faithful unique pseudo expectation property if and only if J can be recovered from the expectation by looking at this, basically the same formula we had before, phi of A star A, look at the image of J in a J intersection B in its injective envelope and then take the double annihilator. And this condition, this if and only if, is automatic sometimes. And so if you have a regular inclusion with a faithful unique pseudo expectation property, if you take any regular ideal, then the quotient has the faithful unique pseudo expectation property. Corollary is in the abelian case, you don't have much to do. It's just a regular ideals quotient has the faithful unique pseudo expectation property again. And lastly, the one I was interested in, really interested in, is if you start with a pseudo-Cartan inclusion and you have a regular ideal, then the quotient gives you a pseudo-Cartan inclusion. So this generalizes what happens in the Cartan case. But that begs the question of what's the Cartan envelope of the quotient. Okay, so I'll write that down. So the initial data is you start with the pseudo-Cartan inclusion, and you have its Cartan envelope, and you have the conditional expectation for the Cartan, and you start with a regular ideal. By the corollary, we get a pseudo-Cartan inclusion, and if you follow the maps giving the isomorphism between the regular ideals of C and the regular ideals of A, you can follow it along. And so what you get is you find an ideal J prime, which is regular, and it's basically the same formula we've looked at before. And so I wind up getting a Cartan inclusion. And so that's a candidate for the Cartan inclusion. The embedding is kind of what you expect. And alpha bar from the quotient to of C by J and the quotient of A by J prime is just looking at what happens to cosets, and it does what you expect. So you get a star homomorphism, and one-to-one, you can you use some of the previous results and you look at it a little bit. But regularity is a tricky thing. You don't know that all normalizers of in the quotient go to normalizers in the quotient of the Cartan, because you don't have a really good description for what the normalizers are in the quotient. But there is a proposition you can prove. So if you start with a pseudo-Cartan inclusion and then any Cartan, maybe it's not a Cartan envelope, but you have a star monomorphism embedding C into A so that that carries D into B. And you also want the ideal intersection property. So the point is, if you happen to know you have a star semigroup that generates C and D, then it, such that the image on that star semigroup lands in normalizers, then it turns out you have regularity altogether. And you don't need the approximate unit property for that. And so my last result is that if you have a pseudo-Cartan inclusion with Cartan envelope and you start with a regular ideal, you form this J prime as I did, then the quotient, together with this embedding I've described, turns out to be the Cartan envelope. And so that generalizes what we did in the Cartan case. So, and that's everything I wanted to say. Yeah, Matt.
These conditions where you have the ideal intersection property, could you replace that with just require that of regular ideals?
I think you could.
Yeah.
I think that's, I think you could just use that.
Do you have it, can you go back to 8 slides?
It's fine.
So here,
Here?
do you have a description of what this carton envelope is for the essential property?
So Diego, say that again. Do I have a description
A
of,
description of what this carton envelope is for the essential C-star algebra of the group?
for the essential C-star algebra of the groupoid?
Is it?
I haven't written that down, but I think you could do that. You can write down the groupoid description if you started having, you can write down the groupoid description based on certain states of C and D. And then sort of follow, you mimic the construction that Kumjin did, using the states that instead of using a conditional expectation, use a pseudo expectation.
Okay, thanks.
Thanks, Stephen.